So today we do the solving of equations. You know, up till now, what we did last lesson was probably new, that you didn't get that kind of those properties of logarithms in Algebra 2. But the first two sections were pretty much what we taught about exponentials and logarithms anyways. And this is new. Right now we're taking advantage of the fact that logarithms and exponentials are inverses of each other to solve equations. And it'll be involved with the simple meaning of the one-to-one property kind of stuff. And then we'll learn more complicated exponential and logarithms and some word problem stuff. So the simple, if it's a one-to-one, then use that to solve. Then what we're going to talk about later, you don't use to solve if it's one-to-one. And sometimes you'll see that sometimes it's one-to-one inside of a problem that's actually much more complicated than that. But if you take, for example, this 2 to the x equals 32, I mean, that is an exponential equation. But if you recognize it for what it is, 32 is 2 to the 5th. And then the one-to-one property says that if 2 to the x equals 2 to the 5th, since the bases are the same, then the exponents are the same. Right? And the same thing would work for logarithms. Right? This one here, it's not a logarithm equals a logarithm, but you could quickly put it into that form. Right? If ln of x minus ln of 3 equals 0, then that means ln of x equals ln of 3. And since the logarithms are equal, then what's inside the logarithms must be equal. X equals 3. Now, as we saw before, it could be that you got to do just a little bit of arranging here, like 1/3 to the x. Well, 1/3 is like 3 to the minus 1. So if you make that change to the left, that makes it 3 to the negative x. And on the right, you recognize 9 is a power of 3 also. That's 3 squared. Then you've got an exponential equals an exponential. They have the same base. Therefore, the exponents are equal. Negative x equals 2, or x equals negative 2. So there will be some that are just like that. Just use the one-to-one property if it'll work. Okay, now if it's not like that, then we have some steps, and they're somewhat similar, right? For exponentials and logarithms, okay? In the first step, always isolate, right? Isolate the exponential, isolate the logarithm. It needs to be the only thing on that side of the equation before you go to the next step. Right? For exponentials, right? Once you've isolated the exponential, you take logarithms of both sides. Right? Because this is finding the composition of a function and its inverse. There's going to be some cancellation that goes on there. Now, it's similar for logarithms. You could say take exponentials of both sides. But in fact, if you're comfortable with changing from the exponential form to the logarithm form, then that's really what you're doing on the second step over here. Right? You isolate the log, and then you convert that logarithm to an exponential. I find that a much more straightforward way to go. Now, once you've done that second step for both of them, there may be some solving left to do on the order of basic algebra, to include sometimes some minor factoring. Right? So you got to finish solving the equation, get the value of x. And while it's always a good idea to check, once you get your answer, plug it back in and see whether it works in the original equation. It's especially important for logarithms, because remember, logarithms don't have an unlimited domain, right? You can only take the logarithm of positive numbers. And if you get a negative, if your value, when you plug it in, leads to a logarithm of a negative number or 0, you got to throw it out. So that's extraneous. Another example of extraneous solutions. So these are going to be kind of what we use to guide us through the basic solving of logarithms and exponentials. So here's an exponential. The first step would be isolate, right? So in this case, what do you have to do to isolate? Divide by 2, right? So divide by 2. So now we've got 5 to the x equals 16. Okay, what does it say to do on the next step? Take logarithms of both sides, okay? But remember, you always got a decision to make when it comes to taking logarithms. What base logarithm are you going to use? Okay, so let's do it like this. I'm going to do it twice. If I take the log base 5 of both sides, then it'll look like this. Log base 5 of 5 to the x equals log base 5 of 16. Now, how does this simplify on the left? If you take the log of an exponential and the base of both of them are the same, then what does that equal? It's x. Remember, that's like taking the composition of a function and its inverse. That's why we're taking the log base 5, so that these things match and we just get x. Okay. Now, the log base 5 is 16. If you're using our calculators here that have the log base, you could put that in the calculator directly. If you're not using our calculators that have the log base, then you might have to use a change of base formula. Something like, what would the change of base formula if I want to convert that to a log base 10 because it's on my calculator? What would it look like? Yeah, the log of 16 divided by the log of 5. Right? And you could go ahead and do that, and you should get a decimal. Log 16. Make sure you end parentheses. 1.723. Okay, now you could have decided, I'm going to take log base 10 of both sides. It would look like this. Log of 5 to the x equals the log of 16. And then you can use power property, right? How would I use the power property to simplify the left side? Bring down the x in front, right? So now it becomes x log 5 equals log 16. X equals, divide both sides by log 5, log 16 over log 5. You know, you never really talk about change of base formulas, but you end up doing the same calculation as we did over here, and you get the same answer. So, I mean, most of the time when we solve logarithms, we really do want to match the base of the logarithm with the base of the exponential. That was the whole point of learning these two things together. Okay, here's another exponential. First step, isolate the exponential by add 7 to both sides. So we add 7. Okay, e to the x equals 30. Next step would tell us to do what? Take a log of both sides. Okay, what would be the log you use? Natural log, because it's exponential is a base of e. We want to use a logarithm of a base of e, which means ln. So that's ln of e to the x equals ln of 30. And then how does this simplify on the left? Ln of e to the x equals x. The logarithm and the exponential base cancel each other out. All you get is x. And then ln of 30, you just put in the calculator directly. 3.401. You know, I took these this coming from a check for understanding underneath the example in the book, and their directions said approximate the result of 3 decimal places. So if it says that, do it. I will say that the calculus teachers ask us to always do 3 decimal places because that's the standard on the AP test. I don't always use 3 decimal places, but it does match up.
What's the rule for the natural log being canceled out?
Remember, we had a property that said log base A of A to the X, and actually A to the log base A of X in either case equals X. Now, in the case of, that means for any base. That A means any base. Okay, well, what if the base is E? Then that property becomes ln of E to the X, or E to the ln of X in either case equals X. It just equals the exponent. So here, ln of E to the X is X, right? Because you don't see it, but actually there is a little base there of E, right? That's what the ln part's telling you. These two match. Okay, here's another one. It's a little more complicated. What's the first step? Isolate by subtracting 4, right? 6 times 2 to the t plus 5 equals 7. Then divide by 6, both sides, right? So this is 2 to the t plus 5 equals 7 over 6. And I wouldn't simplify it. I would leave it like it is. Okay, we've isolated the exponential. Next step would be which log? Log base 2, right? So we take log base 2 of both sides. Log base 2 of 2 to the t plus 5 equals log base 2 of 7 over 6. Right, how does the left-hand side simplify? Right, it equals to the exponent because the base of the logarithm matches the base of the exponential. T plus 5 equals log base 2 of 7 over 6. Okay, now, how can we use change of base formula to do that calculation? You want to do okay. Let's say we use natural logs, right? T plus 5 equals ln of 7/6 divided by ln of 2. And then what would you have to do? You haven't solved for t yet. Subtract 5. So t equals ln of 7/6 divided by ln of 2 minus 5. And you could put all that in the calculator. ln 7 divided by 6 divided by ln of 2 minus 5. Negative 4.778. Now, did you have to use ln at this point? Now, if you did log base 10, you would have had exactly the same number. Change of base formula works, no matter, just as long as those are the same. So it's whatever is the log of that number divided by the log of that number. I will say that one of the common mistakes we make on these kinds of problems is like, I think we've done 3 of them so far. It's like when you take the log of the left because you know you're simplifying, so you can isolate the variable itself, you don't take the log of the right. Like you're going to say, oh, I'm going to take ln of e to the x, and you forget to take ln of 30. Okay, remember, you're doing the same thing to both sides. Okay, now we'll do a logarithm. First step would be isolate. In this case, that would be subtract 7. 3 times ln of x equals -2. Are we isolated? What do I have to do? No. Just divide by 3. Right? ln of x equals -2/3. Okay, now we're isolated. What do we do next? Convert to an exponential. Right? Now, so let's see what happens if I convert to an exponential. Right? What is the base of the exponential going to be? What is the base of the logarithm? So it's e to the what power? -2/3. Remember, the logarithm equals the exponent, so the -2/3 equals x. And that you can put in the calculator, right? Second, e to the -2 divided by 3. 0.513. Now, I think if you looked in the book, the way that they word it, they don't say convert to an exponential. They say exponentiate both sides, right? And by exponentiating both sides, what they're saying is whatever is the base of the logarithm, then we're going to make it e to that power equals e to that power, right? So now I've got 2 exponentials, but what is e to the ln of x? It's just the x, right? So x equals e to the -2/3, which is the same thing. You know, I find it cleaner just to say just convert it to an exponential, since we're probably pretty much okay like that. The other thing is that if you've already written this equation, ln of x equals -2/3, then trying to write in where you are like making those the exponents now of 2 exponentials, I mean, you wrote those at a normal size, not at the size you would normally write an exponent. So sometimes you kind of think, oh, I better make these really big e's so it looks like those are exponents, and just cleaner to make it, convert it to an exponential, and then you're done. Okay, how about this one? Isolate. Okay, FAMO. Okay, we divide 3. Okay, then what? Exponentiate. Convert to an exponential. What will be the exponential? The base will be 4 to the 3rd equals 6x, right? 4 to the 3rd equals 6x. So 6x equals 64. And then that's where, now this is one where there's a little more solving to do, right? We're not quite done yet, so divide by 6. And since we're turning all this stuff into decimals anyways, 10.667. Not too bad? Easy? Okay, here's where we get into exceptions. okay, where it's not just as clean as that. This is a particular one, which if you remember, we have had before solving equations that look like this. X to the fourth minus 3x squared plus 2 equals 0. Do you remember what we called that? It was called quadratic type. Right? It's not a quadratic, but it's going to factor like a quadratic. You just look at the left. You say, what are the factors of 2 that add up to -3? You can say -2, -1. But it's not a quadratic, so it's x squared minus 2, x squared minus 1. Right? That's called a quadratic type. Well, this is the same pattern over here, right? It's e to the x squared minus e to the x, or minus 3e to the x plus 2. I mean, we can rewrite this a little bit if it helps. E to the x squared minus 3e to the x plus 2 equals 0. So if e to the x is like our, in a quadratic, the x term, right? This is e to the x squared. So it is like a quadratic. It is actually, it's quadratic in terms of the powers there. So this one will factor like e to the x minus 2 times e to the x minus 1. Right, the same kind of thinking you do with a quadratic. What are the factors of 2 that add up to -3? Right, that's where these two numbers come from. Right, the -2 and the -1. And then the first term is e to the x, e to the x. Okay, when you factor, you should be able to FOIL and get back to where you were, or distribute, or whatever it is. I mean, what do you get if you say the first terms would be e to the x times e to the x? Right. Okay. E to the x times e to the x. Remember, what do you do with the exponents? You add them, right? So that's e to the 2x, right? That's where that term is coming from, e to the 2x. Okay. And then the others will be e to the x times -1, e to the x times -2. They add up to the -3 e to the x. And the last term, -2 times -1 is 2. So this is, you should recognize the pattern of the exponents, right? It's e to the 2x and then e to the x. So you're going to factor it like a quadratic. Now, you're not done, right? So remember, the reason we factor and set it all equal to 0 so we can use zero product property. That tells us that either e to the x minus 2 equals 0 or e to the x minus 1 equals 0. Right? One of those two has to be true so that the product is 0. So you solve. We now solve each one of those like we've already been solving. Add 2, add 1. So we've isolated the exponential. Then we take a log of both sides, right? Which log? ln, because it's the exponential of base e. So this is ln of e to the x equals ln of 2. Ln of e to the x equals ln of 1. Now, one of those you can do without a calculator. What's ln of 1? It's 0. That's a property we've got, right? So this one, x equals 0. And how about this one? Ln of 2, you just have to turn into a decimal, right? Ln of 2, 0.693. So recognize that particular pattern. There will be one homework anyways on that. It's an exception where it's not just isolate and take logs of both sides. You're going to do a little bit of factoring first. Right? Here's another exception to that rule. Right? And when you start to see all these multiple logarithms around, what do you think you're going to do with that? You're going to combine them using what we did in the homework last night, right? So not only that, think ahead here, right? If I can combine the two logarithms on the left, then I'm going to have a logarithm on the left equals a logarithm on the right. Which property am I going to use then? When you have a log equals a log, the one-to-one property, right? So that's the goal here. I mean, that is one way. You could do it different. You could do it different. But let's say, how would these two combine? Right? It would be a quotient property because of the minus. You'd combine them into one logarithm. The log of 4x over 12 plus x equals the log of 2. And now, since the logarithm on the left equals the logarithm on the right, they're both base 10. What equation can I write down? Yeah, 4x over 12 plus x equals 2, right? One-to-one property. And then that is something you can solve using other means. Multiply both sides times 12 plus x. Four x equals 24 plus 2x. 2x equals 24. X equals 12. I mean, could you have done it different? What if instead of doing that, you subtracted the log 2 to this side, right? Then it would have looked like this. Log base 4 of 4x minus log of 12 plus x minus log of 2 equals 0. Oh, it's not a log base 4. Sorry. I don't know why I thought that. Okay. And then you can combine all three of the logarithms into one logarithm, right, using properties. So log in the numerator will be 4x. In the denominator, since both of those are negative, it'll be 2 times 12 plus x equals 0. So we put them all into one logarithm. That logarithm is isolated on the left. The next step would be convert to an exponential. What would the exponential be? The base of the logarithm is 10. So it'll be 10 to the 0 equals this, right? 10 to the 0 equals 4x over 2 times 12 plus x. But what is 10 to the 0? That's 1. So we have 1 equals 4x over 24 plus 2x. And then when you multiply both sides by 24 plus 2x, you get back to the same old thing. I mean, believe me, when you do the test, there will be problems like this that you guys surprise me with the way you take it, but it's not wrong. You know, you went a little bit different way, but it's okay. And as long as you applied all the properties correctly, it can still work. Right, that was one of the exceptions. Not quite the clean procedures. How about this one? Oh, just a second. What did I not do on this? This was a logarithm equation. What was the last step of solving logarithm equations? To check for the answers, right? I mean, I'm sure we didn't do them on any of these here. And it was not an issue at all. The next one we're doing, it's going to become an issue. But, you know, if you just put in a 12 here, it's positive, 4 times 12. You put in a 12 there, 12 plus 12, it's positive. So there were no issues with that. But now let's see what happens on this one. Okay, which property do we use first? Say again? We want to combine those logarithms into one. Which property we're going to use? A product property, right? Because it's a plus. The sum of logarithms becomes one logarithm of a product. So that's log. It's base 10 x times x minus 9 equals 1. Okay, we've isolated the logarithm. Next. Convert to an exponential, right? The base is 10, so 10 to the first equals x squared minus 9x. So 0 equals x squared minus 9x minus 10. Which I could see that was going to be a quadratic. So I got to get everything on one side, 0 on the other. Then we solve that. Is it factorable? Yeah, it's pretty basic factoring. That'll be x minus 10 times x plus 1, which means x equals 10 and negative 1. Okay, now we check, right? If I plug in x equals 10, log of 10, fine. And the log of 10 minus 9, that's the log of 1. No problem with that, right? Check. But what happens if I plug in negative 1 here? Right? If you check for negative 1, then we have the log of negative 1 plus the log of negative 1 minus 9 equals 1. But both of those are undefined. So that means the negative 1 is an extraneous solution because you plugged it back in and it gave you. It's still undefined. If any logarithm becomes a log of a negative, then you got to throw out that answer. That's why you check. So that is extraneous. I think I got 2 more. Okay, so now that we know how to solve equations, at the beginning of the chapter, when we had a word problem involving an exponential or a logarithm, all you could really do is evaluate. And now we can do some solving. So this one, it says, you invest $500 at an annual interest rate of 5.25 compounded continuously. How long will it take your money to double? Okay, which formula do we use for compound interest compounded continuously? PERT, right? So we need this formula. A equals P E to the RT. Okay, let's plug in what we've got. Okay, we know the initial is $500, that's the P. And the interest rate, 5.25%, which we have to write as a decimal, 0.0525. So this looks like A equals 500 e to the 0.0525t. Now the question is, how long is it going to take your money to double? Okay, well, how much will it be when it doubles? It'd be 1,000, right? That 500 turns into 1,000. Right? Doubling means they equal 1,000. So let's put in A is 1,000. And we are being asked how long, so we have to solve this now for t. So how would I go about solving for t? Okay, we've got to isolate the exponential and take the log of both sides, right? Now we're just doing what we've done in all these other problems leading up to this, right? Now notice what happens when you divide both sides by 500. Right? What do you get on the left? You get 2 equals, I'll show that, 500. 500. 2 equals e to the 0.0525t. So what you notice here is that it didn't really matter what the initial investment was. But what if the initial investment was $1 billion, right? Then the doubled would be $2 billion. But at that very first step, when you divide both sides by the initial investment, what are you going to get on the left-hand side? It's always 2, right? So you don't even need to know the initial investment. How long is it going to take your money to double if you're doing continuous compound interest at a rate of 0.0525? That's it. But then it would be a 3, exactly. How long will it take for your money to quadruple? 4, there you go. Okay, now we've isolated the exponential, so next we take the logarithm of both sides, right? So the ln of e to the 0.0525 t equals ln of 2. Okay, but ln of e means 0.0525 t equals ln of 2. Right, that's why we did it. But we haven't quite solved for the t. What do I have to do? Divide, right? So t equals ln of 2 divided by 0.0525. T equals 13.203. So it would take 13 years to double your money. Not too hard? Okay. And then we'll do a logarithm. Right? The retail sales in billions of dollars of e-commerce companies in the United States 2002 through 2010 can be modeled by this equation right here. Okay? What is this? It's the domain, right? It's not part of the equation. It's the domain. It's telling which values of t you can have in this function. That's domain. Okay. Where t represents the year, with t equals 12 corresponding to 2002. Okay, so which year was the 0 year? If 2002 was t equals 12, which year was the 0 year? 1990, right? During which year did the sales reach $80 billion? Okay, so what are they expecting us to do here? Substitute the 80 billion where? For the y, right? Y is telling you the amount of money as a function of how many years, right? So we're going to go 80 billion. Are these in billions? In billions. So 80 billion equals negative 566 plus 244.7 ln of t. Okay, so now this is a logarithm equation, and we're going to solve it like we solve a logarithm equation, which means first step is isolate. Okay, what should I do to isolate this? Add the 566 to the side, just to make that 646. Okay. And then we're going to divide by 244.7, right? All right, so now we have ln of t equals 646 divided by 244.7. I'm not going to simplify it yet. I'll just do it all at one time. Okay, what do we do now? We've isolated the logarithm. Convert it, exponentiate, or convert to an exponential, right? What is the base of the logarithm? It's an e, right? So this will be t equals e to the 646 divided by 244.7. And that you could put in the calculator. Second, e to the x, 646 divided by 244.7. I'm getting 14 0.0127. Okay, so during which year does the sales reach $80 billion? In 2004, right? 2002 was the year 12, so we're in year 14, 2004. So this was the word problem for number 11, right? They used a different number there. So I used the one that they had as the check understanding. So you can see they do it with their own value there. Okay. So that's it. So by the simple equations, more or less, it means a one-to-one. If you could do a one-to-one, do it one-to-one. If not, right, you solve exponentials by taking logs to both sides. You solve logarithms by converting to exponentials. There are a few exceptions, quadratic type, having to use the properties from last lesson so that you can solve. So that is it.